If the nature of science is to better our understanding of the world and the universe we see around us, shouldn't science be for everyone? Dr. Chanda Prescod-Weinstein is a theoretical cosmologist who, along with being a world expert on dark matter and dark energy, is a vocal advocate for making science accessible for all. This episode, I got to speak to her about the nature of the universe, how it began, how it will end, and how we can make physics a more welcoming place for every citizen of planet Earth.
I'm Chanda Prescod-Weinstein. I'm a theoretical physicist who focuses on dark matter primarily and other questions in early universe cosmology. And I'm currently an assistant professor at the University of New Hampshire in the Department of Physics and also core faculty in Women's and Gender Studies.
Fantastic. Thanks very much for speaking to me today, Chanda. I always think it's sort of worth when you're talking to a theoretical physicist or a cosmologist, I always sort of want to sort of nail down exactly what those terms mean. You know, what actually is sort of theoretical physics and cosmology, and how do they actually help us understand more about the universe?
Yeah, I keep thinking I'm going to get in trouble for responding to this the way that I do, but I actually would say that I make things up for a living. I mean, and so, you know, in physics, we have like the experimental work, like going out and actually collecting data and trying to, you know, or in astrophysics, doing observations, like looking at galaxies, looking at stars, looking at Mars, which we're doing a lot of right now, right? But we always have to try and make sense of this data with mathematical models. So we're both interpreting the data through mathematical models, like we're using Newton's gravity or Einstein's gravity, depending on the length scale that we're dealing with. If we're looking at if we're looking at a galaxy, we're probably using Newton's gravity. If we're looking bigger than a galaxy, we might be using Einstein's gravity. So that's where theoretical physicists come in. Einstein was a theoretical physicist. He came up with a model through which we interpret the data and helped explain some of the data. And so, for example, special relativity really came about because there was this Michelson-Morley experiment that was showing that the speed of light was constant no matter what your frame of reference was. And part of Einstein's strength actually was looking at that experiment and taking it on its face value. Like, if the speed of light really is constant, then what does that imply about how the world works? And so then he used math to build a model.
Awesome. Yeah, and so, I mean, to me, that sort of, you know, sitting down and working things out and thinking about things, there's sort of like it's quite romantic in a way, in sort of the way that philosophy is, would you say?
Yeah, I mean, I was going to say about like what Einstein did, particularly with special relativity, right? It's always like this very famous story that, you know, he was working as a patent examiner. He didn't actually have a job as an academic. And it's kind of like metal. Like what he did was he was like, I'm just going to think about this. Everybody has this idea of how the problem gets solved. They're completely wrong. Here's my idea instead. And so I really think that there is something very romantic about it. There's something, and in general, thinking about cosmology, which I should probably clarify for listeners. When I say cosmology, we think about the origin and evolution of spacetime and pretty much everything inside of it. So it's kind of like, it's like science on the largest possible scales. And in some sense, like the deepest questions, like I'm a practicing Jew, and I basically think that like my job is to figure out like the physics version of Bereshit, which is the beginning of the Torah. So and I like to think about it as storytelling. So I'm a voracious like fiction reader, and you know, what's cool about it is that it's real. But it can be like just as fantastical as like some of the fantasy fiction that you'll read. And you know, just as carefully constructed as like, you know, a good sentence out of, I don't know, Jane Austen's Mansfield Park or something like that.
Yeah, I mean, do you think with regards to the story of the universe so far, do you think that relatively speaking, we actually know a decent amount, or do you think we're still really in the dark?
It really depends on how you look at it. So, you know, in theory, we know like everything that everything in the universe is made of. So we know that all of the matter energy content in the universe is either dark energy, dark matter, or what we would call normal matter, like the everyday stuff like us. But I have to put like normal in air quotes because it's only about 4% of the matter energy content in the universe. So actually, like, humans are not just abnormal because we're from Earth and there's only one Earth. We are also abnormal because pretty much everything in the universe that you can see is actually a very small percentage of the matter energy content in the universe. Everything else is dark matter and dark energy. So in that sense, we know a lot about the universe. The only thing is we have no idea what dark energy and dark matter are. So like we have like really good like names for them, but we don't know what they are. So I think it really depends on, whether you like the rug that you have just swept all of your ignorance under.
How do you sort of on a day-by-day basis go about solving those problems like dark matter and dark energy?
Yeah, so that changes depending on what professional stage you're at. So as a professor, which I guess I'm the US equivalent of a lecturer, I think in the UK, right? So I have a research group that's working with me. At this point, I have 3 graduate students, I have an undergraduate, and I also have what we call a postdoctoral researcher. So this is someone who already has their PhD and is basically in preparation to start applying for faculty positions. So a big piece of my job is actually managing that research group and all of the research problems that they are all working on. So each of them is working on a problem that either we have come up with together, or if they're more on the junior side, maybe something that I assign to them as like, okay, I want you to figure out how to write this code that will do this calculation with a dark matter candidate. And then let's see what happens when we do that calculation. So the cool part is getting to come up with ideas. And also actually there's just like a huge educational component, which is guiding young people through the process of learning to become independent researchers. So that's a big piece of what I do. In theory, if there weren't so many administrative pieces to being a faculty member, in theory, I do math all day, but actually I really have to make sure that I carve out time in my schedule to make sure that I actually get to sit down and do some math.
So with that, I suppose, we sort of, at least in theory for the moment, know what the universe is made of in terms of visible matter and dark matter, and then the dark energy driving the quickening of the expansion of the universe. But what about beginning of the universe? How close are we actually, understanding exactly what that was like? And the other thing that I always think has to come with that question is there a before the universe?
Yeah, so this is like I almost want to tell you to call up the students who were in my cosmology seminar last semester, because they actually gave me like a bunch of trouble about the Big Bang.
Right.
I think that the intuition that people can come to the Big Bang with is that it's like an explosion. Like, I guess, our best intuition for that is a bomb going off. I don't particularly like thinking about bombs, but let's say that's our intuition, is something like blowing up. But the Big Bang isn't, if it was a thing, isn't quite like that, because it's really a moment in time that happens everywhere in space. And so it's not one place in space where everything explodes and then fills space. So that's one version of events. It is also the case that the more research that we do on early universe cosmology, and the more that we understand what we call the inflationary universe. So when the universe was less than a second old, space-time expanded exponentially. The more that we understand the mechanics of how that might have happened, the more that it seems like a likely scenario that lots of different bubbles of space-time pop off at the same time. And so it may be that we're just in one bubble of space-time, and that there are other bubbles of space-time, and that maybe bubbles of space-time have been forming eternally into the past and eternally into the future. So this model is called eternal inflation. And I wouldn't necessarily say there's complete consensus on eternal inflation, but there are a lot of people who take eternal inflation seriously. And so it may be that there wasn't really ever a beginning to the universe, but rather that there is, many beginnings to different parts of the universe, and that that's something that's always been happening and always will be happening. There's a complex question there, which is like, is that a testable idea? It's something that comes out of the math, right? So you study the equations, and the equations kind of point in that direction. But there's always a question there, which is, how do you test it? And if you can't test it, is it still physics? And there's lots of debate about this. Sir Roger Penrose feels pretty strongly that it has exited the physics corner and has entered into the philosophy corner, right? I disagree with Sir Penrose, but I also think, first of all, he's just like a super lovely man, and he's made such significant contributions to physics that he's allowed to have his opinions,
It's really interesting there, because you've mentioned space-time a few times, and I always wonder, why are those two concepts intertwined in astrophysics? Is it that one can't exist without the other? Like when you talk about space-time, why is that?
So, going into the early 20th century, certainly what we would call like professionalized physics, professionalized science, thought of space, like the three dimensions that we like exist in every day, was conceptually like a completely different thing from time, which is this thing that's actually really hard to define. Like we all kind of have an intuition for time. Even just like looking at our face every morning, we're like, oh, time has happened to my face, right? So I think everybody has an intuition for time, even though it's actually a really hard thing to define physically. And we don't actually have a good explanation in physics for why it only goes in one direction. There are some hints from thermodynamics in relation to like, entropy can only get bigger in one direction. And actually, English physicist Julian Barber has a really beautiful book out right now called The Janus Point that is actually getting into this for people who are curious about theories of time. But one of the things that happened, just going back to that, that Michelson-Morley experiment that found that the speed of light was constant no matter how you looked at it, was that Einstein realized that taking that experiment seriously meant realizing that space and time actually mix. And so you can't actually treat space and time separately, even though on the scale of our everyday lives, they feel pretty separate. But also our guts are not actually good at writing down physics theories, right? So just because something feels a certain way doesn't mean that our gut is super accurate, right? That was one of the revelations of special relativity, was that space and time are not actually separate, and we have to think of them as one unified concept as space-time. And that was certainly borne out even further when, about 10 years afterward, Einstein wrote down general relativity. And I think it's, and I guess I'll just say, for people who are like, yeah, but how is that relevant to my everyday life? If you have used like Google Maps or Apple Maps or anything that relies on GPS, GPS needs general relativity to work. So this is actually part of your everyday life, even if you're not really conscious of it being part of your everyday life.
I really love all that, and it's just really sort of mind-expanding thinking about all those things. But I suppose that brings us nicely on to your book, which is really why our paths have crossed. Because you're at the time of recording, your book is about to come out in the UK. It's called The Disordered Cosmos. I was wondering if you could talk a little bit about the title. What's that reference to?
Yeah, so the title comes from was inspired by the very first research paper that I ever published with my PhD advisor, Lee Smolin. So we were particularly concerned with this question that you were mentioning earlier, cosmic acceleration. So the quickening of the expansion of the universe, which is currently happening right now. So there's the inflationary era in the very early universe, when the universe was less than a second old. And then billions of years later, the expansion of the universe starts picking up pace again. And I'm interrupting myself. Some of us think that we have come up with a good explanation for this in the form of something called the cosmological constant, which is just that there's this like constant dark energy that is all pervasive on large scales. I have never really been satisfied with that solution, and a lot of people are still not satisfied with that solution. So part of my work as a PhD student was actually trying to come up with different ways of solving this problem. And so the very first paper was taking the idea of non-local connections that can happen in quantum gravity models, particularly in loop quantum gravity and spin foam. Those are the two models. And seeing how those energies could be connected to something that looked like a dark energy. And because these were non-local connections, they were disordered. And so when I was a PhD student, I started writing a blog called The Disordered Cosmos. And so when it came time to write my first popular science book, I was like, there's no better title than the one that has worked for me for so many years. So in some sense, that's really where it comes from. But I also think, the book is a holistic look at the doing of physics, both from what we know about physics to also the social experience of being within the physics world. And my understanding of what it means to be a physicist has been very disordered. And so I think it also reflects kind of the way I've kind of bounced around and understanding what is it I'm doing here and what are the things that shape the life that I'm living.
Yeah, that's one of the things that really comes through in the book. There's sort of this merging of cosmology, and then I suppose what you might sort of umbrella as like critical theory. You talk about your experiences of being a young Black girl growing up in America and discovering a love for physics. What was it like when you were a young girl, sort of realizing that you had this love for physics, and did you find that you had many scientific role models?
Yeah, it's interesting because the book is not like a memoir in any sense of the word, and so I always feel like I had like such mixed feelings about the ways in which my story, in incomplete pieces, becomes part of the larger narrative as a launching off point. So I saw a documentary about Stephen Hawking called A Brief History of Time. It was made by Errol Morris when I was 10. And I should say, actually, contextually, that at the point that I saw the documentary, and that documentary was like, that was why I decided to become a theoretical physicist. I was like, this is so cool. I can get paid to do math for a living, and also math can help me describe the universe. And I knew that I loved to do math. I was also at that point, this was the spring of 1993, actually recovering from having spent time going to school in London. And I have never hated school as much as I did during the time when I was at school in London. And a big piece of that was the racism I experienced on the schoolyard. The white kids wouldn't talk to me. So, and there were very few brown kids in my school. And so I was very isolated. I felt like I was bullied by the teacher. The teacher was constantly threatening to put me on report for things that my mom was asking for. Like I didn't have control over it. I was like a 10-year-old. So I think I was actually at a very precarious moment where I could have started to unplug a little bit from being someone who was academically inclined, because I felt really discouraged from that time. And so I really think in some sense, and this is a story that's not in the book, right? Because it's not particularly relevant to the larger points that I'm making. But I think in context of your question, it's valuable to say that I think the documentary helped me kind of write myself as someone who was still interested in academic work and who was really excited about math. And that actually, I think it was important to see someone like Stephen Hawking, who didn't fit the norm in a lot of ways, who was still doing it. And so I think the message very early on was, you don't have to be like everybody else to be a theoretical physicist. You don't have to be anything like Einstein to be a theoretical physicist, which I think for American kids of my generation, older millennials, Einstein was the quintessential genius scientist figure, right? And Stephen Hawking was in many ways nothing like him. And I think that was in terms of having role models. No, I had never heard of a Black physicist at that point, and I don't think I heard of a Black physicist until I went to university.
Yeah, I mean that was one of the things that struck me when I was actually reading about the book, is that I read that you are one of fewer than 100 Black women to earn a PhD in physics. And I think like a lot that would really shock a lot of people. I think that that number is so low. Do you think that we are in the science community is in any way sort of making progress in terms of addressing that imbalance?
Yeah, so I guess I should make the statistic a little more specific. So there are under 100 Black American women who have PhDs from departments of physics. The number, shifts a little bit if you include astronomy or if you include people who are doing physics work in material science departments. And then if you add biophysics in, the numbers change significantly because biophysics is really a different track. Like they often don't come through physics programs. And to kind of add further context to that, in the United States, there are 2,000 PhDs granted in physics every year, right? So 100 Black American women in all of history versus 2,000 every year, even though we're like 6.7% of the US population. So the numbers don't really add up, right? It is the case that the number of PhDs per year inches forward most of the time. There's like one more or two more than there were the year before. But progress is incredibly slow, and the rate of progress is too slow to reach equity anytime soon. The number of Black students who are earning bachelor's degrees in physics in the United States, the share has actually been declining over the last decade as opposed to increasing. There's a whole report out about why this has happened, but I think like to first order, one of the big changes is that a lot of historically Black colleges and universities, what we call in the United States HBCUs, have closed their physics departments, and they were for a very long time producing the majority of Black bachelor's degrees in physics. And what we would call predominantly white institutions have just like not picked up the slack. So I think people should be shocked by the numbers. And I actually think one of the other shocking things, I did my PhD in Canada, is that outside of the United States, countries aren't even tracking this information, right? So at least in the US, we can point to these numbers and say, we can quantify the extent of the problem to some sense. That doesn't mean we know all of the reasons why it's happening, but we can quantify it. In Canada, there has been no data collection around this to date. I think that the Canadian Association of Physics is set to release their first data set that will cover some of these things in June. I know some students in the UK have written to me asking, like, where did I get these statistics about the US? And I explained our National Science Foundation actually tracks this information. Our American Institute of Physics tracks this information. So I do think that now there is some pressure on the UK's Institute of Physics to start collecting this data. I suspect that when we get the data for both Canada and the UK, that the numbers will actually be worse. And I don't mean absolute numbers, I mean percentages, right? That the share of the population that should be getting the degrees versus who's actually getting them is going to be worse.
Yeah, and it definitely sort of makes you think back about when you sort of track the history of astronomy and science and astrophysics, and which you sort of allude to in the book as well. As you were saying, the sort of quintessential astronomer or astrophysicist in people's minds would be a white man, essentially. If we're sort of considering like the perhaps lack of diversity in science historically, I was wondering to get your thoughts on if you were just to consider sort of discoveries and the maths alone, how different do you think our knowledge and our understanding of the universe would have been if we hadn't had that lack of diversity over the past hundreds of years? Do you think we would have arrived at different conclusions differently and look at the universe in a different way?
Yeah, I mean, and I think, again, I can make that more specific, which is like a white guy of a specific class, right? Like it's only relatively recent that even in, for example, the UK, that people from the working classes have been like welcome to attend university and have actually been able to rise through the ranks. And there continues to be a problem there, even for white working class students, right? And so these barriers are kind of multifaceted. They're not just racialized or gendered, but they're also classed. I think the laws of physics are universal. I don't think that Black people are going to come up with different laws of physics than white people are or anything like that. But I do think we have a ton of data that says diverse organizations are more competent than homogenous organizations. And so maybe we would know more. And I also think that the kinds of questions that we ask are always socially contextual, right? And I think that sometimes people feel like this is more obvious in the social sciences. And I'm, certainly, particularly, I think this jumps out in a parliamentary system. Like the Tories and Labour have very different agendas, right? And so that is going to shape what kinds of questions the government decides to prioritize. Like these are the things that we really need to do right now are probably going to be different coming from a prime minister who's a Tory and a prime minister who is from Labour or, from the Lib Dems, if something like that were to ever happen. I think that government funding actually shapes how we think about science a lot. And so who is actually there, not just as a scientist in the room doing calculations, but also who is in the room having the conversation about what are our priorities as a society when we're thinking about spending money and providing funding. And this really filters down that, I don't know what the age range of the listeners is going to be, but when I was a kid, going to university in the UK was free. And so I actually, at one point, it was decided that I would stay in the UK for high school because my family thought I would have a better chance at actually being able to go to university and afford it. And in the time since then, right, fees have skyrocketed and there are all of these conversations about how to handle debt and that kind of thing. That all of those things then shape who is in the room doing science, who feels like they have the choice to pursue an A level doing this versus doing that, where they think they'll get their highest score and which university they think will take them based on those scores. All of those things are going to shape who ends up in the room calculating, right? And so it's not necessarily about discovering that the laws of physics are identity dependent, but certainly there's a social aspect to who gets to be in the room to calculate how many people can afford to be in the room calculating, right? And then also what our priorities are, who is willing to fund you to do what.
It's also interesting there. You're sort of saying about the laws of physics being the same everywhere, because if we were just going to sort of track back to cosmology for a bit, that was one of the things I was going to ask you, is that are the laws of physics actually the same everywhere? Do we know that they're the same everywhere, like forever in throughout the sort of observable universe?
So there are certainly experiments that look for evidence that there's some kind of spatial or time dependence of certain physical constants in nature. But so far, all of the enormous amounts of data that we've collected are fairly consistent with the fact that the laws don't change. There may be limits to our understandings of the law, so maybe we don't have the law of gravity completely worked out. But everything is beautifully self-consistent. I think that's actually one of the things that makes as the child of political activists, the world of politics and social justice organizing is extremely messy. And there's something beautifully organized about the fact that we can tell this coherent story about space-time from point A to point B. And sure, there are questions along the way, but we do have this incredible tapestry that of equations that are generally consistent, that seem to work everywhere. They work whether we're looking at it through a telescope or we're looking at it through an electron microscope. And that's pretty awesome.
Yeah, indeed. It sort of always reminds me of the way I first felt when I heard that, Carl Sagan's Blue Dot speech. All your sort of all the sort of trivial stuff that you worry about during the day, your day-to-day basis, it all just melts in the background when you read something like that. And I always think that, astronomy and astrophysics and cosmology and this understanding of the wider universe, it's a real leveler, isn't it?
Yeah, I love you putting it that way, that it's a leveler, because I do think that the one thing that all human societies have had in common throughout history is that they've looked at the sky and told stories about it. And I think that what I'm doing is a version of that. I'm looking at the sky, I'm telling stories about it. I happen to think my story is a very good one and empirically well tested, right? But nonetheless, I think what ultimately appeals to me about it is the story. And I think, the reason that people pick up like I'm a columnist for New Scientist, right? And I was like really pleased to find out before I became a columnist that my dad was a subscriber to New Scientist. And actually, like the last time I visited his flat in London, he had it sitting on the table, right? I just think that we like that story. I think it's part of who we are. The philosopher and theorist of science, Sylvia Wynter, articulates humans as a storytelling species, that we are a biocultural storytelling species, that is actually as much a part of who we are as some of the other things that we might consider to be like more physical. And I think that that's right. And in some sense, that what I'm doing is very human. And it should be a great leveler. It should be something that we can all say, okay, we have this thing in common with each other, that we are fascinated by the night sky. I think that for this reason, it also raises really interesting and vital ethical questions about what it means to change the night sky. For example, launching so many satellites that the night sky no longer looks like what it did to our species for the entire time we have been evolving. We have evolved with this night sky, and I think in that sense, it is actually part of who we are.
Yeah, definitely. I suppose the difference, you just going back to what you were saying about the storytelling aspect, the difference between, sort of cosmology and a Jane Austen novel is that we know how the Jane Austen novel ends. So I was going to ask you, what are those sort of unsolved mysteries about the cosmos that you would, if you could click your fingers and know the answer to, or is that sort of taking the fun out of it, clicking your fingers and immediately knowing the answer?
I think that one of the challenges that we face as scientists, and certainly that students of science face, is that being a scientist is actually about what we don't know. It's not about what we do know. I think that the way that it gets taught in school and even in university, you're handed a book, the book makes a bunch of statements about things that we know about the universe, and then you close the book, and it does have that kind of feeling of like, and then like, Fanny and Edmund end up together at the end of like, Mansfield Park is always going to be my reference point, right? You do get that kind of feeling of a story that has a beginning, a middle, and end from textbooks. But that's not actually what science is like when it comes to the practice of science. And that can be a hard thing for students to absorb because it means getting comfortable with not knowing what you're doing, because part of being a scientist is being confused. If you're not confused, then you're probably not working on something that like really requires any more work because you know all the answers already, right? So I do think that the irony maybe a little bit is that it does seem that humans, and I'm really truly not an expert on this point, it does seem like humans struggle with uncertainty. And I don't know if that is maybe a reflection of the type of society that I live in. I live in a highly mechanistic society that likes the idea of things being very firmly predictable. I have an equation, I plug in the conditions I have now that allows me to predict the conditions I will have in 10 minutes. People like that kind of certainty. And science simply doesn't have that kind of certainty built into it. It's a social problem in some sense, because like governments are always asking us, well, like, what will I get out of it? And I'm like, well, I'm not sure what you'll get out of it, but I know that like we'll get something out of it, but I can't tell you what that will be right now.
Yeah, I suppose that also links into that entire question. How will the universe end? Can it end? Like, could everything end?
Yeah, so I feel like on this point, I just have to refer everyone to Katie Mack's incredible book, The End of Everything, because she's basically written an entire book that's basically about the different scenarios that the ending of the universe can have. And I guess like maybe I'll make a little bit of like a personal sociological comment here in mentioning that book, which is that Katie and I first met as prospective PhD students back in spring of 2003. And so it's actually like a real pleasure to be able to, almost 20 years later, cite her book and to have my book coming out the year after her book came out. Partly I just want to like be like, Katie, we made it. but also that it's such a wonderful thing to now be in a time period when I can point to another woman's book and say that that's actually your reference point for these scientific questions. I personally try not to think too much about what's going to happen to space-time, particularly if cosmic acceleration keeps going, that eventually the night sky will start to be a little more drab compared to what we see now. I think like the good news, and I'm kind of making a face as I say this, is that, the sun isn't going to last forever, and our solar system is probably going to get destroyed before things get really boring. But I don't know if that's like really heartening, because then like if we do manage to sort out this global warming situation, we are at some point going to have to get ourselves off Earth.
Yes, indeed.
That's like, I feel like I have to say for the audience, it's like 5 billion years into the future. So like we have much more pressing concerns to deal with like right now, which I would say like to first order global warming is our biggest existential threat.
Yeah, indeed. Well, on that rather ambiguous note, I think that's about all the time we have, Chanda. But thanks very much for speaking to me today, and good luck with the book, which is coming out here at the time of recording in about a month or so. And yeah, thanks very much for speaking to me today.
Yeah, thank you so much for having me.